In this podcast, we're going to talk about molecular formula and degrees of unsaturation. This is a topic from Chapter 10, but we're going to introduce it a little bit early because it's very useful when we're talking about spectroscopy to know how to calculate degrees of unsaturation. First of all, what is degree of unsaturation? Well, alkenes, alkynes, and cyclic compounds are unsaturated hydrocarbons because they have fewer than the maximum number of hydrogens per carbon. The maximum number of hydrogens per carbon is CnH2n plus 2. And this is what we have when we have a non-cyclic alkane. So CnH2n, that's the maximum number of hydrogens per carbon. And so a non-cyclic alkane is considered to be saturated. Now, if we take that alkane and we put it into a ring, we change the formula here. Now we have CnH2n. So we've dropped 2 hydrogens. Let's see how that works. Let's try a 3-carbon chain here. That is C3. Let's count hydrogens. 1, 2, 3, 4, 5, 6, 7, 8. That's C3H8. Now, if we take 3 carbons and we put them into a ring, now we have C3, and we have 1, 2, 3, 4, 5, 6, C3H6. We've dropped 2 hydrogens. If we take that same straight chain alkane and we add a double bond, we also drop 2 hydrogens. So we have CnH2n. And let's take our 3-carbon chain and we're going to turn one of the bonds into a double bond, and you can see we have C3, and if we count hydrogens, we have 1, 2, 3, 4, 5, 6, C3H6. If we have a cyclic alkene, we drop 2 more hydrogens and we have CnH2n minus 2. How do we know that? Let's draw a 3-carbon chain. Let's put that in a ring, and then let's add a double bond. And as you can see, we have C3. 1, 2, 3, 4, C3H4. So every time we add a ring or a pi bond, we drop by 2 hydrogens. And so the general formula for a hydrocarbon is CnH2n plus 2 minus 2 hydrogens for every pi bond and or ring in the molecule. And the total number of pi bonds and rings in the molecule gives the degrees of unsaturation. So if we go back and look at the ones we've already drawn, we can see that the cyclic alkane has 1 unsaturation because it has 1 ring. The alkene also has 1 unsaturation, and the cyclic alkene has 2 unsaturations. So we can call this unsaturation number would be 2. We could call it degrees of unsaturation. It has 2 degrees of unsaturation, and we could also say it has 2 units of unsaturation. And so given the molecular formula, we can tell the degree of unsaturation. Let's see how this is done on the next page. Let's see. For a compound with molecular formula C5H8, give the degrees of unsaturation and draw a few possible structures for this compound. So C5H8. If saturated, it would be C2n plus 2, so 5 times 2 is 10 plus 2 is 12. It would be C5H12 if it was saturated. We have 4 less hydrogens than 12, don't we? And therefore, we have 2 unsaturations. So 2 hydrogens per unsaturation. So if we want to look at some possible structures, we're going to look for things that have 5 carbons and 2 unsaturations. So those 2 unsaturations, we could have 2 rings, we could have 2 double bonds, we could have a ring and a double bond, we could have a carbon-carbon triple bond. A carbon-carbon triple bond is 2 unsaturations. And what you're going to find is drawing possible structures is going to be so much easier than it was in Chapter 1 when you had to count the hydrogens. As long as we have the right number of unsaturations, then we will automatically have the right number of hydrogens. So that's a 5-carbon chain with 2 double bonds. We could have the space between the double bonds. We could have it look like that. I'm not going to draw every single possible structure. I'm just drawing a few here. We could have a ring and a double bond with 5 carbons. We could have a 4-membered ring with a double bond and a bond hanging off like that. We could have carbon-carbon triple bond. 1, 2, 3, 4, 5 carbons. We could have the triple bond be at the end. So it could look like that. Many, many possibilities here. We could even do a 3-membered ring like that. This process can be extended to molecules that contain heteroatoms such as oxygen, nitrogen, and the halogens. So we're not limited to hydrocarbons. If we have an oxygen in our molecular formula, we're going to ignore the oxygen. If we have a halogen, we're going to replace each halogen with a hydrogen. And if we have a nitrogen, we're going to subtract 1 hydrogen for each nitrogen. So let's look at an example of each of these on the next page. All right, so let's say our molecular formula is C5H8. Okay, so we know that we need to ignore oxygen. So our working formula is C5H8. And we're just ignoring oxygen to calculate units of unsaturation. It still is part of the molecule. So we have C5H8. If saturated, it would be C5H12, wouldn't it be? 5 times 2 is 10 plus 2. C5H12. We are short by 4 hydrogens. Therefore, we have 2 unsaturations. So 2 hydrogens per unsaturation. Let's draw a possible structure. There are many possibilities here. I'm going to draw a 5-membered ring. And I'm going to draw carbon-oxygen double bond. That would be 2 unsaturations. 1 for the ring, 1 for the double bond. Let's try one with a halogen. So it says halogen, replace each halogen with a hydrogen. So let's do that. So our working formula here, we have C6H12. C6H12, if saturated, it would be C6H14. Okay, so we're down 2 hydrogens. We are short 2 hydrogens. Therefore, we have 1 unsaturation. Alright, so I'm thinking, I guess I'm in the mood to draw rings today. I'm thinking a 6-membered ring with a chlorine hanging off. Might be a possibility there. So that's one possible structure. There are many more. But that one looks good. Alright, so this one here, this last one, we have a nitrogen and an oxygen. We're ignoring oxygen. And we are subtracting 1 hydrogen for each nitrogen. Alright, so our working formula here is C8H12 H8. If saturated, that would be 8 and 8 is 16, 17, 18. That would be a whopping 18 hydrogens, C8, H18. We very clearly aren't anywhere close to that if we take 10. If we take 18 minus 8, we get 10 hydrogens. We are short 10 hydrogens. So therefore we have 5 unsaturations. And I'm going to give you a little hint here. When we're drawing possible structures, if we have not very many carbons and a lot of unsaturations, a good idea is to draw a benzene ring in your structure as a potential structure. So we have, let's do a benzene ring. A benzene ring is one ring and 3 double bonds, so that's 4 unsaturations. We've already used up 6 of our carbons. Let's add 2 more carbons, and I'm going to do, since I have an oxygen, I'm going to do a carbonyl, and then I have 1 nitrogen left to handle here, NH2. Okay, so that's automatically going to be the right number of hydrogens because we have the right number of unsaturations. But just as a check, let's make sure. Let's count hydrogens. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. That's exactly what we're looking for. Alright, now there is a quicker way to do this, if you'd like. It's shown on the next page, and that's you can use the formula. Now, I don't use the formula because I'm not very good at memorizing formulas. But this is a much faster way to do it, and what I'm going to do is include this formula on the test so you don't have to memorize it. But let's show how this works. So the formula is U for degrees of unsaturation, and that's equal to 2C plus 2 plus the number of nitrogens minus X minus the number of hydrogens divided by 2. Alright, so let's redo that C8H9NO using the formula, and you'll see this is a little quicker. U equals 2 times the number of carbons, that's 8, plus 2, plus 1 nitrogen, minus X, there are no halogens, so that's 0, minus 9 hydrogens, divided by 2, and if you calculate that, we get 5 unsaturations. Voila! Same exact number, so you can use either method, both are fine with me.